Welcome to today's Explainer. We are stepping straight into the future of medicine through the 2026 framework of Lázaro López Paz. We're going to deliberately unpack the white paper on quantum sensors, biosensors, and quantum simulation for medicine and neuroscience. Now, this is highly technical territory, so we are going to take our time to parse the exact mathematics, logarithmic functions, and mechanical equations that make all of this possible.
Okay, let's dive into this. We're using a zoom-out structure for this analysis. We'll be scaling all the way from subatomic equations in quantum physics foundations up to OPMs, organ on a chip, quantum drug simulation, and finally reaching the macroscopic level with clinical AI integration.
Section 1. Quantum Physics Foundations. This is where we lay the subatomic bedrock that actually makes this technology a reality.
Let's start with the foundational math behind nitrogen vacancy centers. The governing principle here is the Zeeman effect. The formula, delta E equals G times mu sub B times B, describes exactly how energy levels separate depending on an external magnetic field. And this is what establishes our resonance frequency, F equals delta E over H. Simply put, the external magnetic field dictates the energy gap, acting as the ultimate subatomic translator in this Hamiltonian model.
To put that translation into perspective, the specific gyromagnetic factor for these NV centers is exactly 2.8 times 10 to the 10th hertz per Tesla. It's a massive constant. And it's exactly what allows us to take extraordinarily faint magnetic fields, like the whisper of a firing human neuron or the human myocardium, and translate them into highly measurable optical frequencies.
That brings us to the sensitivity equation. Eta represents the standard deviation of magnetic field measurements over time, specifically sigma b over the square root of t. Why does this matter so much? Because this precise logarithmic metric allows us to rigorously evaluate successive improvements in both NV and hexagonal boron nitride quantum sensors as the technology matures. Moving up the scale, we reach Section 2, OPMs and neuromagnetism. This is where we focus on early detection. Let's walk through OPM polarization dynamics step by step. First, dynamic polarization dP over dt balances the optical pumping rate against the magnetic field's depolarization. Second, this dynamic translates directly into measurable light intensity over time. Finally, we linearize this around an operating point. The main takeaway here is that a microscopic change in a magnetic field causes a direct, perfectly measurable flicker in light.
Now, what's really interesting about these mathematical models is how we handle arrays of these OPM sensors when placed over a human scalp. We map neuromagnetic fields into very precise data structures. We start with a data matrix mapping specific channels and times, extract the channel mean, and calculate the covariance matrix. This rigorous math acts as a topological map, showing us exactly how different regions of the brain synchronize in real time. From those matrices, we calculate the effective propagation velocity. We take the physical distance between two brain regions and divide it by the time delay of neural firing events between them. If this velocity decreases significantly over time, it serves as a highly sensitive early biomarker for neurodegenerative diseases like Alzheimer's or Parkinson's, completely detectable long before physical symptoms ever manifest.
Scaling up again, we transition to Section 3, Organ on a Chip and Biosensors, the microscale.
In these microphysiological cellular environments, this exact differential equation models concentration dynamics. It mathematically isolates a drug's elimination rate against its source function over time. This allows us to precisely simulate exactly how a compound metabolizes in a human organ, entirely contained within a microfluidic chip. We can contrast two integrated biosensor models here. The electrical FGFET sensor relies on threshold voltage and total capacitance to measure activity. But look at the immunoinfrared signal equation on the right. That formula calculates the basal signal against pathological protein folding. It specifically isolates dangerous beta-folded protein fractions, like amyloid beta, floating within the fluid. To actually translate those raw quantum sensor signals back into real-world biology, we use biomarker calibration models. Whether we apply the logarithmic model for concentration, the Langmuir model for antibody binding, or the inverse estimation function, these formulas act as the vital bridge. They take quantum signals and convert them into precise femtomolar concentration estimates for blood biomarkers.
Next, we move to Section 4, Quantum Drug Simulation. This is where we simulate the actual molecules targeting these neurodegenerative biomarkers.
This brings us to the VQE molecular Hamiltonian.
It's a second quantization mapping of single and double electron integrals. The crucial thing to understand here is that classical chemistry computational models completely fail at this level of complexity. But advanced quantum hardware? It can map these fermionic operators directly to Pauli matrices, bypassing classical computational limits entirely. Let's see how this builds into the complete VQE quantum simulation pipeline. Step 1. Calculate the classical integrals. Step 2. Map the Hamiltonian to the hardware qubits. Step 3. Define the unitary coupled cluster ansatz. 4. Execute the eigensolver on the hardware itself. And finally, Step 5. Optimize classically to find the minimum energy state. This exact 5-step protocol is what makes simulating delicate drug-binding energies possible.
Zooming out to the macroscopic level, we arrive at Section 5, Clinical AI Integration, the systemic platform.
This AI platform is where it all finally comes together in clinical practice. It concatenates these completely distinct mathematical models into a single predictive feature vector. It pulls propagation velocity from the OPM MEG, concentration and folded fractions from the biosensors, electrical resistance from the organ on a chip, and binding energies from the quantum simulation. All this unified data trains the artificial intelligence to classify patient risk states with absolutely unprecedented mathematical rigor.
It's important to neutrally highlight the author's commitment here. Lázaro López Paz notes that this entire systemic framework is offered as an open base. It is fully reproducible and improvable by the international scientific community under a Creative Commons 4.0 license, ensuring open-source collaboration across all 7 interconnected projects.
We'll leave you with this final provocative thought from the framework. What are the profound ethical and theological implications of literally reading the human heart and mind at the quantum level? It is a staggering reality that leaves us to quietly consider the ultimate systemic impact of this technology.